All right, ladies and gentlemen, the recording of class has started. All right, on Friday, we started talking about the behavior of waves in certain situations. And we talked about reflection, where a wave's going to come in, it's going to bounce off of a medium that it can't pass through. And then we talked about refraction, where as a wave goes from one medium to another, its speed changes, and then depending on the angle that it hits the new medium, you might see a bend in that wave. And then we talked about diffraction, where waves can pass through an opening, and when they do pass through an opening or around a corner, they'll spread out, and that energy will be carried around the corner, even though it might not be in direct line. Okay? Those are all behaviors. Those are all things that waves do sort of on their own. Okay? Is this where we left off?
C.
Right? Okay. All right. So today we want to get into more wave interactions. What do waves do when they encounter other waves? And that's really where we're headed today. Okay? All right. You good there? Okay. The first part of wave interactions starts with superposition. Okay. When we did the Slinky Lab, superposition is down at the bottom right next to diffraction.
Oh.
So when we did the Slinky Lab, there was a situation where we shook the Slinky, and I was standing on one end, and I shook the Slinky, and Maddie was on the other end, and she shook the Slinky, and those two waves traveled through the Slinky, and they ended up meeting each other in a certain spot. What did we observe happen to those two waves when they met each other in a certain spots? They switched sides when one wave went down, hit your hand, and bounced off the other side, right? But when we made two waves, what happened? Say again?
Did they go like so?
No.
And then part of it continued toward Maddie, and then another part of it bounced back towards you.
That happened when part of it bounced off towards me and part of it continued on to Maddie. That's when the one wave was traveling and encountered another medium, okay, when we changed springs. But this, we were both in the same spring, we both made a wave, okay?
Same
Well,
spring.
let's talk here, okay? Yeah, same spring, okay?
That's right.
So let's talk about this picture right here, okay? So these, anybody know what these are, actually?
Is that what project down like this?
Yes.
Oh, wow.
Yeah.
I didn't know you were
Those
talking
picture
about.
reels that go.
So picture wheels, they're called slide projectors.
The
Okay.
trees.
So back in the olden days, this is how we used to project slides. Okay, or big pictures. We didn't have PowerPoint, so sorry, that made me sound really old right there, but I apologize. Anyway, so here's the picture, and these two are projecting light. They're projecting different colors of light to make a picture, and they're set up in a way that the two beams cross each other on the way to the screen. But if you look at the top picture, right, it's still showing this nice blue sky, and this picture on the left is still showing this nice field full of yellow flowers, okay, even though those two colors passed each other as they went through. Is there any change in either of the pictures because they crossed through the other beam of light? They look exactly the same, even though they passed through that light on the way to the projector. Why? Because these are waves. And what did we say that waves were? Disturbances that carry what? Energy, right? They're not what? They're not matter, right? Everything in the universe is either matter or energy. They're not matter, they're energy. Meaning, we can have two waves occupying the same place at the same time. Why? Because like we said, what are they?
Just energy.
They're just energy. They can pass right through each other and cause no change in each other whatsoever. Okay? Waves are matter, not energy. That means they can be in the same place at the same time.
Just
Waves
mixed
are
up the
waves
words.
are
Oh,
not.
sorry. Waves are energy, not matter,
There you go.
like it says there on the screen. And that means that they can pass right through each other. Now, these are light waves, and that's the case, but it's true of sound waves, it's true of waves that you make in slinkies and whatever, okay? In fact, some of the things that we do out there in the real world depend on this. For example, kind of musical arrangement, whether it's a rock band or whether it's an orchestra, requires that more than one wave can be at the same place at the same time. When you listen to a musical ensemble, when you listen to a rock band or whatever it is, you hear guitar, drums, and bass all at the same time. If you could only hear one of them at a time, it would sound funny, right? If you heard the guitar play a certain part of the song, and then the drums played a certain part of the song after that, because you can't have guitar waves and drum waves at your ear at the same time, wouldn't work, right? We have to have, in order for certain things to work, those waves have to occupy the same place at the same time, okay? Does that make sense? Okay. Then, going back to your question from before, that was when you shook your wave up and down while I was shaking mine side to side, right? And they're passing right through each other, and they don't interfere, they don't mess with one another as they go through. But certain things will happen when waves do interact with one another. And to get that, let's get ourselves a picture. Okay? All right, so here's me. I'm down here on this side. Sure. Here's Maddie, she's down here. And here's our slinky that connected us together. Okay. So I made a disturbance in this slinky. I shook it in this direction, made a disturbance that, in the case of this picture, so that disturbance is facing downwards. Okay? Maddie shook the slinky in a different direction and made a disturbance that goes this way. And because of the way that they were made, this disturbance travels down this way, this disturbance travels down this way. The whole way, the whole time, these disturbances are traveling through the slinky, right? This coil makes the next coil move, and then this coil makes the next coil move. And then with Maddie's wave, this coil makes the next coil move, and then this coil makes the next one move, right? We pass the energy on, one to the next, to the next, to the next, okay? But when we get to this spot right here, what's happening? My wave moves by making the spring move which way?
To the right, down.
Well, to the right, but what does it do to the spring itself?
It pulls it out.
It makes it move downward, pulls it down.
I'm sorry. I don't know what's going on. I don't know how to work my phone.
I see. Use those two buttons on the side, just turn the volume down. You know, that'll help.
The volume is off.
So,
Nice, Maddie.
I was just thinking about that, like, how can it go with
so at this spot, right, my wave moves by pulling the spring downward. Maddie's wave moves by pulling the spring which way? Up. So if we get to a point where they meet and they're at the same place at the same time, my wave is trying to pull the spring down, Maddie's wave is trying to pull the spring up, what will be the end result?
it balances.
It's not going to stop. What's the spring going to do at that point? It's not going to do anything, right?
Oh.
Now,
Rest position.
rest position. Now, does that stop the wave?
No.
No, doesn't stop the wave. It just means at that point in time, right, those two waves cancel each other out and nothing happens. Okay? But if we have a situation where, I shake the spring in that way and it makes it go towards the bottom, and then Maddie also makes it go towards the bottom, right? Travel here, right? Now what's going to happen to the spring at that point? It's going to go down, but how much? Even more. Could be twice if we knew what about these two waves. If they had the same amplitude, okay? But more generally, we're going to see an increase in the amplitude of the waves. Just at that point, right? And then once they pass through each other, does anything happen? They don't affect one another, but at that point, we would see a greater amplitude. We call this idea interference, where two waves can occupy the same space at the same time, their amplitudes are going to combine. Generally, we refer refer to that idea as interference. Now, the two pictures that show up next, they did not copy very well. So you might have to draw yourself a little cartoon, kind of like I was drawing with me and Maddie in our springs, right? The first, actually this is the second instance that we talked about. One type of interference is called constructive interference. Two or more waves combine to form a larger amplitude. So in these pictures right here, these are like little still motion pictures of a spring as two waves are traveling through it. These two arrows right here, these two red arrows, represent two waves. The one on your left is traveling towards the right. The one on your right is traveling towards the left. Okay? The place where the yellow arrow is where they meet. What do you see about the amplitude of the wave at that point in time?
It's
Pretty, you know, maybe it's more generally it is what?
larger.
Larger. It's bigger, right? Because both of those waves are trying to pull the spring upward. Okay? Any guess what we call the other example? Destructive interference, right? So, in this case, right, here's my two waves, the two red arrows. This wave on the left traveling towards the right. This wave on the right traveling towards the left. When they get to where the yellow arrow is, what do you see about the amplitude of the spring at that point in time?
Rest position.
It's pretty close, right? It might not be exactly rest position because what do we see about those two waves?
These are hard to draw.
They're not exactly amplitude, right? Now, you don't exactly have to draw these pictures like they have up here, right? Draw what I was just drawing on the board, right? And that's, I mean, it's the same idea, right? Another important thing to sort of keep in mind, if you look at the pictures after the yellow arrow or below the yellow arrow, right? You can see that the two waves, after they come out of the interference, look exactly the same as they did before, right? Like this picture down here, you can see those two waves, right? After they've interfered with one another, they look pretty much exactly the same as they did before they interfered with one another. Is that good? Constructive interference, destructive interference. Do we need a couple more seconds to finish up our awesome drawings? Louise, go ahead. Sure. So constructive interference, we get a bigger amplitude. Destructive interference, we get a smaller amplitude. Okay, go ahead.
Wait, so constructive would be the one where it's the two opposite, the waves on the opposite sides.
That would be what?
Constructive.
Because if they're on opposite sides, right, one's trying to pull the spring up,
Oh,
the other one's trying to pull the spring down, so they cancel each other out, right? Maybe not fully, but they end up with a smaller amplitude. The constructive interference is going to be when they're both on the same side, because they're both trying to pull the spring in the same direction, and that gives you the bigger amplitude. Alright. Are we good with these? Okay. Lights.
Camera.
Alright. Becca. Either one. Whoa, whoa, whoa. Okay. Alright, so, like we just talked, okay, so I make this wave, right, it goes down, it bounces off Becca's hand, it comes down, bounces off my hand, back, forth, back, forth, back, forth, back, forth. That's just reflection, right? But if I make one wave, it goes down, it bounces off Becca's hand, starts coming back towards me, and then I make another wave, those two waves are going to interfere with one another, right? So, I go here, then I go here, right? We'll get all kinds of craziness where some parts are big and some parts are small, right? So we're getting a bunch of constructive and destructive interference that is happening all throughout that spring. But if I create waves at just the right frequency, okay, every time I shake this spring, it's going to go down and bounce off Becca's hand and come back towards me. But but the next time I shake the spring, I'm creating a new disturbance. It's going down, and it's now traveling towards Becca, while the other wave is traveling back from Becca. Okay? And if I shake it at just the right frequency, I can get this. Okay? All right, so next. See that spot like right in front of your face? Yeah. Okay? It's not really in front of his face for recording purposes. Okay? So what is the spring doing at that spot right there?
It's staying like flat.
It's pretty much nothing, right? So Max, what has to be going on at that point in time?
That's where they're meeting.
That's going to be what kind of interference?
The destructive.
That's destructive interference, okay? But in this case,
Interruption, just one quick announcement.
better be quick.
Spring cleaning tickets will be sold this week in lunch, up to Thursday for $10. T-shirts also available during lunch for $10 through Friday. Tickets will be available through Thursday, shirts through Friday. Thank you.
Okay, next. See how much I'm moving my hand? Okay? I'm moving my hand about this much, right? That's true. Right? It's not meant to be a replacement for class, just a supplement. Okay? So, but if you look at the waves that I'm creating, right, what do you see about the amplitude of the other parts?
Very large.
Very large, much larger than how much I'm moving my hand, right? So what has to be happening at that point in time?
They have to be adding.
What kind of interference?
Oh, it's
That's constructive interference. It just so happens that these waves are being created at just the right frequency, that the constructive interference keeps happening at the same spots, and the destructive interference keeps happening at the same spots. Okay? So here, let's do this. All right? If I increase the frequency to a greater frequency, all right, I can do this. So now, right, there are several spots where the spring is sitting still, right? Keenan, there's one right in front of you, right? Okay. Then there's one right in front of Max, and then there's one right in front of Sarah here too, right? Okay. Those are all places where what's going on? Destructive interference, right? And then the other places are where constructive interference is occurring, right? If I change the frequency, you just hold on. All right? If I change the frequency, I can do this.
No way.
So now we're seeing multiple places where the destructive interference is occurring, right? And I'm just, okay, got it back. Right? So multiple places where the destructive interference occurs, and multiple places where constructive interference occurs.
Wait, is
Okay, go
that
ahead.
a standing wave?
Okay, so here, why don't we just bring this together here? There we go. Okay. So those are all examples of. I'm glad you just. Those are all examples of what we call a standing wave. Standing waves are a combination of reflection and interference that results in a wave that looks like it stands still. Reflection because those waves have to go off, bounce off Becca's hand, and come back towards me while I'm making the new waves so they get interference, right? We said that there is both constructive and destructive interference occurring, okay? The place where destructive interference occurs is called a node, a point where the medium has no displacement from rest position. So we said if it's got no displacement from rest position, that has to be destructive interference. But the other places are called antinodes. I know that's anti is kind of a negative connotation, right? But nodes are where the destructive interference occurs. Antinodes, constructive interference. Hold on a second. Hold on. Let me finish this picture. There's one more slide. So in this picture of a standing wave, right? These places here would be nodes. Hold on a second. Good shot.
So tired of that.
Is that like
There's a reason why they kind of have the same thing. That these places are nodes, especially the one in the middle. Now, in the one that we made in class, obviously the end can't be a node because I'm shaking it up and down, up and down, up and down. Okay? But then these places here are the antinodes. Okay? Now, something to be familiar with, something not to get confused on. Okay? There are not 4 antinodes in this picture. It's not the top and the bottom are the antinodes. That whole section is one antinode because it doesn't have a top and a bottom at the same time, right? It goes up and down, then it goes down and up. Does that make sense? Okay? So this is only 2 antinodes, not 4. All right. Quiz tomorrow. Take a look at the pages from your book. Take a look at the questions from your book. Open note over the 2 outlines we did and the slides.